Hey everyone, this is Darsh. So for my thesis, I'll be working with Professor Franz and Professor Admir on the carbon cement supercapacitor technology for energy storage. And my specific task will be to take this to the next level by scaling this technology. So I'll be talking about a little bit of the background and then how I will branch off into my own project to scale the technology that the lab is developing. So starting with some motivation, as we know, with climate change being the problem of the century. We need sustainable energy sources, but one of the drawbacks for these currently is how the sources aren't reliable 24/7, such as you can't have solar energy at night and wind patterns can shift throughout the day. So you need reliable energy storage that's also cheap to counteract that demand. So as you can see, sometimes the direct energy sources at night during peak demand hours isn't enough. So you need some kind of energy storage that can use the energy collected during the downtime to use during peak hours. So that's our main motivation, especially given that current solutions on the market, such as lithium ion batteries, have some disadvantages. First of all, they're expensive, and as I'll show in a map later, that they're hard to extract. They aren't found everywhere across the globe. So they have some advantages, how they have very high energy density, and low leakage of the voltage, and they're reliable. But they age over time really quickly. In your iPhone, you see your battery degrading after 3 years. So that's a no-go for residential applications. They're expensive. So we can try to find new technologies where we trade off some of those advantages, such as energy density, to make up for everything else, if we have enough volume to store the energy. So that's where our technology at EC Cubed of carbon cement supercapacitors comes in, where we use a volumetric wire of nanocarbons within a cement or concrete structure to store energy through a supercapacitor mechanism. So this is the structure where you have two electrodes that we make with our special carbon cement, which basically we mix nanocarbons into cement as it cures. Then you have a pore separator for the electron carriers, charge carriers to exchange through that layer. And then you can connect that to your power source, whether it's a solar panel, wind, or any sustainable source. And then you can also connect it out to your outlet that'll be using the energy. And one challenge with the structure is that you need to encapsulate it all in electrolyte, which carries the charge and stores the actual chemical energy. So we can see from there this alternative that also has several other advantages. Um, uh, as you can see on the map on the left, cement is widely available, carbon black as well is widely available, whereas lithium and cobalt, which is used in the state-of-the-art batteries today, is only found in a few spots, which makes it pricey and also hard to scale because cement's already harvested all around the world. So this will be easy to scale if it becomes a reliable technology. Secondly, it's a hydrogen fuel byproduct, so it can have a secondary role in sustainability. And also it provides structural support because it is a strong material still. So if you have it within a cement structure, it can provide you energy storage as well as actual structural support. So you're also cutting down some costs on concrete that you'll be using anyways. So recent work that our lab has done has optimized for what kind of carbon black you use in the actual volumetric wire. So you have different like surface area to volume ratios, which is the specific surface of these nanocarbon blacks. And you can use different types for different applications. So for energy storage, a certain smaller surface area is better. And for resistive heating of like sidewalks to melt snow, let's say, you can use a higher specific surface. And also just using other variables such as the cement to water ratio. You can tune the electrical tortuosity, which is like how much the volumetric wire is percolating throughout the material. And that can optimize the amount of energy that you can store. So the what we've been doing this semester is working on just like different use cases for this technology. So on the left, we have a slab that can use resistive heating as like a sidewalk to melt snow. And then we've been using the same material but with different nanocarbon blacks for energy storage to make these carbon cement cores. And the one in the middle, we can use that on like a bridge prototype, which is what I'm actively working on. And we also use those same cores to make a single cell that can be used as a brick. Moving forward, my goal is to scale this technology on for a larger scale use case. Try to, maybe get a 120-volt outlet that can output that level of charge as a normal residential building out of a wall. And also, as we scale this product, the one thing we're worried about is shrinkage. So we want to, before we make the bigger prototype, I want to prepare and measure the shrinkage of this material, because as you scale the dimensions, the shrinkage is going to get worse. And that's when it starts having a real effect. So we have to prepare for that. And I'll be using the ASTM standards for that. And if there is a lot of shrinkage, then my project will focus on solutions for it. And also, as we scale to these large scale use cases, I want it to be seamless with current building techniques. So if we can use existing concrete blocks that are already very cheap on the market, and then you add the electric core in between those holes in the concrete blocks, it would make the integration of this technology into existing techniques very seamless. So yeah, my primary goals are to create a usable large scale prototype that can, have a classic use like 120-volt outlet. Um, ensure that there's an ease of integration into existing construction techniques and existing materials that are very common and found everywhere around the world. Measure and resolve shrinkage before scaling, because as we scale it, that problem becomes more evident. And also optimize for strain, because we found that because it's soaked in electrolyte, if we squeeze the material a little bit, it can increase the conductivity. So that might just be very easy to do with the wall because the weight of the entire material uh, it creates like strain that can squeeze it together to make the energy storage higher. So we're hoping to understand that a little better as well and see how we can optimize it. So yeah, that's all, and I'm excited to keep you guys updated.